Okay, today we're going to talk about energy, and this is going to lead into our car crash rubric because this is one of the main topics that we're going to be talking about. So energy. So the definition of energy that we are using is the ability to do something or work. That something is work. So work is to apply a force over a distance. So work equals force times distance. So if I'm pushing against the wall with all my might, I'm not doing any work because I'm not moving. There's no distance. So there are two main types of energy. The first is potential energy, and that's the energy that's stored within an object which has the potential to do work. It's the energy of non-moving objects. So in potential energy, work is not being done because the objects are not moving. There's no force being applied over a distance. There could be a force that's being applied, it's just not occurring over a distance. And if you think about it mathematically, if we were using a force of 2 newtons and a distance of 0 meters, 2 times 0 is 0. The second kind of energy is kinetic energy, and this is the energy that an object has as a result of being in motion. So this is moving energy. So in this case, work is being done because the force is being applied over a distance. So if we look at the ball, right at the top of the hill, it has potential energy. And as it's being pushed down the hill, that potential energy is being converted into kinetic energy. So potential energy and kinetic energy have an inverse relationship. So as potential energy is at its highest point, kinetic energy is at its lowest point. So if potential energy is at 100% because that ball is at the top of the hill and it's not moving, as that ball is rolling down the hill, potential energy is decreasing and kinetic energy is increasing. So then when there's 100% kinetic energy, which is when this ball is at the bottom of the hill and it's rolling, it's at 0 potential energy. So the way that we calculate potential energy, the formula is mass times gravitational acceleration times height. And mass is measured in kilograms. Our gravitational acceleration is meters per second squared, which if you'll remember, we said was that constant of 9.8 meters per second squared. And our height is being measured in meters. And the units for potential energy is joules. And one thing that you do need to be really careful of is that the mass needs to be in kilograms. So when you're using our balances, right, the mass is measured in grams, so you have to convert, so you have to divide that number by 1,000. Potential energy is affected by height. So if we have the 4 soccer balls, which soccer ball has the most potential energy? So this one, because the higher an object, the more potential energy it has. So again, this one has the least potential energy, this one has the most potential energy. Where did that energy come from? It came from whoever picked up the ball. So whoever's holding the soccer ball, they're transferring their energy into the soccer ball. Potential energy is also affected by mass. So if we have objects that are all at the same height, one is 10 kilograms, one is 20, one is 30, one is 40. The more mass that an object has, the more potential and energy it has. So the 10 kilogram object has the least potential energy. The 40 kilogram object has the most potential energy. Right, again, they're all at the same height. So where does that energy come from? In this case, the more mass that an object has, the more gravity is pulling on the object. So in this case, the energy is being transferred from gravity. So is it possible for two different objects to have the same potential energy? For example, we have a bowling ball. So if the bowling ball has 20 times more mass than a golf ball, then the golf ball will have to be lifted 20 times higher than the bowling ball to have the same amount of potential energy. So 20 times less mass, 20 times more height. This one has 20 times more mass, so it has 20 times less height. So here their potential energy is equal. So let's talk about kinetic energy. How do we calculate kinetic energy? Kinetic energy, this should say kinetic energy, not potential energy, is also measured in joules. And the formula for kinetic energy is 1/2 of mass times the velocity squared in meters per second. Again, you need to be careful because that mass is in kilograms. And you're squaring your velocity. So whatever the velocity is, if it's 10 meters per second, you need to square it. So it would become 100 meters per second. The shorthand, you'll see the formula, KE equals 1/2 mv squared. Remember, you're squaring the velocity and not the entire problem. So the only number that you're squaring here is that velocity. So this is where your order of operations comes into play. So kinetic energy is affected by speed. So potential energy is affected by height. Kinetic energy is affected by speed. So if we have two cars, one car is traveling at 90 miles per hour, and the other car is traveling at 60 miles per hour. Okay, it's the exact same car. The car on top has more kinetic energy, so this car has more kinetic energy because it's traveling faster. So again, that is the most kinetic energy. That one's the least kinetic energy. It's also affected by mass. So just like potential energy is affected by mass, kinetic energy is affected by mass. So we have a dump truck and we have our smart car. They're both traveling at 60 miles per hour. So which one has the most kinetic energy? The dump truck has more kinetic energy because it has more mass than the little smart car. So although they're traveling at the same speed, the dump truck has the most kinetic energy because it has more mass. And your smart car has the least amount of kinetic energy. So it is possible for two objects of different masses to have the same kinetic energy. But how? So we have our dump truck and we have our smart car. If we're assuming that the mass of the truck is 10 times greater than the mass of the car, so the kinetic energy of each should be the same if the speed of the car is 10 times greater than the speed of the truck. And this is, we're not taking into account friction. So we're just putting friction to the side and we're looking at the two cars mathematically. This dump truck is 10 times the mass. Sorry. So it needs to be traveling 1/10 the speed. Smart car has 1/10 the mass of the dump truck, so it needs to be traveling at 10 times the speed. So if we assumed that this truck was, just for easy ease, right, 10 kilograms of mass, so 10 times 10 would be 100, or 1/2 the velocity squared, right? So we're going to end up with the same amount of kinetic energy. So the rules of how different variables affect an object's energy. So potential energy, just to sum it up, is affected by height and mass. As height increases, potential energy increases. As height decreases, potential energy decreases. So they have a direct relationship. Kinetic energy is affected by speed and mass. So as speed increases, kinetic energy increases. As speed decreases, kinetic energy decreases. Mass affects both potential and kinetic energy. As mass increases, both potential and kinetic energy increase. As mass decreases, both potential and kinetic energy decrease. Remember, energy can be transformed from one type of energy to the other. And again, remember, this is that inverse relationship that we've talked about in the past. So as potential energy is high, kinetic energy is low. And as potential energy increases, or decreases, kinetic energy increases. So there can be a point where they're even. And then as potential energy is at its lowest point, kinetic energy has increased to its highest point. So again, this is called that inverse relationship, and we've talked about that in the past. So if we're looking at the car as it's going down the hill, at the top of the hill, it has the most amount of potential energy. Kinetic energy is at 0. And as it goes down, its potential energy is decreasing, and its kinetic energy is increasing. So at the top of the ramp, the car is at its highest point, and it hasn't started to move. So it has 100% potential energy. As the car's height decreases, its potential energy decreases. And you can watch that here. As the car goes down the ramp, its speed increases, causing the car's kinetic energy to increase. So you can watch the speed increase right here. So the total amount of energy doesn't change because of the inverse relationship of potential energy. So if we start out with 10 joules of potential energy and 0 joules of kinetic energy, right, that's going to increase. So you could have 9 and 1, 8 and 2, 7 and 3, 6 and 4, 5 and 5, 4 and 6, and you get the point. Right, and so here we have a frozen, like a freeze frame of a soccer ball. Here it has 100% potential energy and no kinetic energy. So you can see the amount that potential energy has decreased is the same amount that kinetic energy has increased. Here potential energy has increased by half, and so kinetic energy has taken that half. And then here we are at 100% kinetic energy and 0% potential energy. So we're going to look at a couple animations, and that will show you potential and kinetic energy. So if we take this girl, we'll give her the small can, and we make her climb the ladder. So what we're looking at is the potential energy and the kinetic energy of the can of paint, not of the girl. So as she climbs the ladder, the potential energy increases. Right, it only increases to 50%. Why is it only 50% and not 100%? Well, that has to do with the mass of the can. If she went higher, she could get it to increase more. So we dropped the can of paint. You saw the potential energy decrease, the kinetic energy increase. And we made a mess. Now, if we look at the potential and kinetic energy of the large can of paint, which is affected by mass. We watch her climb the ladder. You can see the potential energy is greater because it's affected by mass. So she's at the same height as she was with the smaller can of paint. Her potential energy is increased. We dropped the can of paint. We saw the potential energy go down. We saw the kinetic energy go up. And we made a nice mess in the process. Now, we look at the potential energy and the kinetic energy of the person on the roller coaster. We can see different points where the potential energy is at its highest, up here on the top of the hill, and at its lowest on the bottom of the hill.